The objective of this video is to understand how the transport layer security protocol works bit by bit. And more specifically, we're going to focus on the client hello first and then move on from there. So I suggest you go to this site, tls.ulfheim.net. That way you can explore a little bit on your own. But to start, let me go ahead and read a little bit about what Network World has to say about TLS. TLS is a successor to Secure Sockets Layer Protocol, or SSL. TLS provides secure communications on the Internet for such things as email, Internet faxing, and other data transfers. For this class, we're really focusing in on the fact that TLS is used when you want to make an HTTPS connection. The S right there standing for security. So you're either using SSL or TLS in this connection to get to whatever website you're trying to get to. And since this is a class really focusing on networking, this part right here is particularly important. It is a good idea to keep in mind that TLS resides on the application layer of the OSI model. This will save you a lot of frustrations while debugging and troubleshooting encryption problems related to TLS. Understanding how things work at the low level is very helpful. And as you can see in this video, this is a little different than you may be used to from me, but I have a series of questions here for you to follow along and answer while we go through this process. So let's begin by clicking Client Hello. This is the first group of bytes that the browser sends to whatever server you're trying to connect to. So when I go to my browser and I type in something like this URL, docs.google.com, before any of this stuff starts popping up, first, this client, my computer, says hello to the Google server. So this is in hexadecimal. You should know that if you're watching this video. And when I click annotations, it'll break down each of these bytes. Remember, hexadecimal, one digit makes half a byte. The first set of ones and zeros that the client sends to the server is called a record header. The author writes, TLS sessions are broken into the sending and receiving of records, which are blocks of data with a type, a protocol version, and a length. And I didn't write that as a think, write, share. I probably should have put something like, where before have we learned that there's a certain terminology applied to certain groups of bytes? In our other networking lessons, we learned that this is called a frame. When you have the original data with a transport layer data like UDP or TCP, and then an IP set of data plus a MAC address. When you have all that data combined, we call this part of the transfer process the frame. And then over here is the packet. Over here, this is called a segment. And then here you have the original data that you're trying to send in the first place. But my actual first think, write, share is, what do these two bytes mean? 0301. So I go over here, and this says 160301. All right, if I go down to here, 0301, this is the protocol version, also known as TLS 1.0. So again, the client is sending this to the server, so the server knows what version it's working with. The first byte is just a thing saying, hey, I'm going to use a handshake record to begin communicating with you being the server. And there's nothing really significant about this number 16 other than this is just the encoding that servers know to begin a handshake record. If we go up here, the whole client hello session is broken down into these 6 things. First, the protocol version, and then we're going to send some random data, which will be used later in the handshake, and then we're going to send an optional session ID time to resume. Okay, if that's optional, it's optional. Next up is a list of cipher suites that the client can accept, and then a list of compression methods that the client can accept, followed by a list of extensions that the client is looking for. Okay, so walking you through this byte by byte, question by question, the protocol version is the first bit of information I want you to write down. Next up, it says how large is the payload, and the hint is that the byte associated with the payload, this number, the hexadecimal number A5 is actually the answer I'm looking for. When you break A5 down into a regular number, it comes out to be 165. So the payload that this whole message is going to be sending is 165 bytes. If I go back here, right here at A5, if I counted all these, it should come up to 165 bytes. Okay, let's count that together. I'm just kidding, we're not going to count that together. And this is going to pop up often is the length of what's about to come next. So that's a pretty intelligent way to design things, to design protocols, where if anything short of 165 bytes comes through, if anything short of that occurs, then there has been some problem with the transmission and the whole client hello process will need to begin again. And since we're talking about electricity and the speed of light, that's not actually too big of a problem. If you're interested in coding stuff, it says the version is 3.1 TLS, which is 1.1. All right, that's confusing, but this is how things are. Instead of the expected 3.3, TLS 1.2 is the max that this client can accept, apparently. It says, looking through the Golang crypto TLS library, we find the following comment. So this is the programming that makes the TLS possible. The TLS protocol possible, and it's written in a Golang. So if vers is exactly 0, we're going to be looking at a variable receiving the value of version TLS 1.0. And the comments are that some TLS servers fail if the record version is greater than TLS 1.0 for the initial client hello. So not all servers can handle anything fancier than 1.0. So all the data following this header of the payload, the header is 5 bytes long. So all data following the header payload is begins here. So the next set of bytes, there's 4 bytes here. This is the handshake header. Each handshake message starts with a type and a length. So real systematic here. The first byte is a value of 1. This is the handshake message type, known as client hello. Maybe we can start saying hello to each other in class by putting up the number 1 with your index finger, not any of your other fingers. And then the next 3 bytes is the length of the payload following this. So this is really cool. This is 161 bytes. If I go up here, at this moment, this was 165 bytes. So all I have to do is count down by 4. So 165 here, 164, 163, 162, 161. So the question is, how large is the session ID? All right, haven't read anything about the session ID, so I'm not answering that question yet. Going down to the next few bytes, 3 and 3, this is the client version. The protocol version is 3.3, meaning TLS 1.2 is given. This choice of version number 3.3 rather than 1.2 is due to TLS 1.0 being a minor revision of the SSL 3.0 protocol, so thus being assigned version 3.1. I did some research into this, and we're transitioning from SSL into TLS. Once that becomes official and accepted everywhere, we won't have to worry about this 3.3 number anymore. Alright, so here's the first set of string of bytes that we get to see. It says the client random provides 32 bytes of cryptographically secure random data. In this example, we've made the random data predictable to make it easier to recognize. So 0, 1, 2, 3, 4, and it just moves on as so. The TLS 1.2 spec says that the first 4 bytes should be the current time in seconds since 1970, but this is now recommended against as it enables fingerprinting of hosts and servers. Okay, finally we're getting to the question. It says session ID. The client can provide the ID of a previous TLS session against the server, which it is able to resume. For this to work, both the server and client will have remembered key information from the previous connection in memory. Resuming a connection saves a lot of computation and network round trip time, so it is performed whenever possible. Once the first client hello goes through, we're good to keep communicating until somehow the connection is terminated, and both server and client knows that session is terminated. Right now, this is the first one, so it's 0. Okay, so for the next set of bytes here, it's pretty long as well, and that's because they're giving the server a choice between all kinds of different cipher suites to choose from. Previously in my computer science class, we had learned about the different ways to symmetrically encrypt data so that we could asymmetrically encrypt that data later. RSA is probably one of the most famous of these cryptographic algorithms that the computer can use. More about that later. Just know that these are all kinds of different ways to create a cipher that the server is going to get to pick from. So whichever number the server picks, we will know when the server talks to us back. So how are the cipher suites ordered? Okay, I have to actually read this paragraph now. It says the client provides an ordered list of which cryptographic methods it will support for key exchange, encryption with that exchanged key, and message authentication method. So if I got to pick and the server is okay with it, I would pick this way first. So RSA for the key exchange, that's a public key exchange way. How encryption with that exchanged key will occur, and message authentication method. So the next question here is number 5. What is the suite represented by 0035? So I just go over here, find 0035, and that's going to be RSA AES 256, and it's a SHA way of authenticating. Remember up here it says, the client provides an order list of cryptographic methods. It will support for first key exchange, then encryption with that exchanged key, and finally the message authentication method. So here we go. Key exchange, encryption method, authentication method. If you want to know more about this, just Google hashing and the concept of hashing. Moving on to question number 6, why can't data be compressed after encryption? So right here, this is the value to show that there is no compression, and that makes sense because of what it says. Compression has characteristics that can weaken the security of the encrypted data, so this feature has been removed from future TLS protocols. The way you compress things is you look for patterns to repeat in smaller bits. If your encryption method has patterns to it, that is not good because then the encryption could be broken pretty easily. In class, we talk about frequency analysis and how in the human language, or the English language, which is human, the letter E pops up at the highest frequency. So if I encrypt something with a simple Caesar cipher, chances are if I could just find the letter that pops up the most, that letter is actually an E, and then maybe I can unravel the encryption from there. So no compression for encryption. Number 7 says, why would bytes 0012 and 0010 need to exist? So let me go over here and comb through. Kind of hurts your eyes to stare at this many bytes, but once I find it, I'll have the answer to that question. Here's 0012 and 001. So it says extension signature algorithms. As TLS has developed, it has become necessary to support stronger signature algorithms, such as SHA-256, while still supporting earlier implementations that used MD5 and SHA-1. This extension indicates which signature algorithms a client is capable of using. So this byte says the number of bytes of the extension data will be following. So then when I go to the extension data bytes, it says there's 16 of them. So the client, can accept any of these types of signature algorithms. So why would these bytes need to exist? I would basically be saying these bytes exist just so that we know nothing is getting lost in transmission. And for the final question, what stood out overall about the client hello? This is really just for you to answer. This last bit really isn't that impressive, so you can say anything you want to answer that last question about the client saying hello to the server for the first time.